This video explains how to answer the age-old question, how many pixels can I hook up to this controller? Well, it's a little complicated and your results may vary. I'm going to try to give you as much background and information to make a good, concrete, informed decision as possible. So first, let's just start with, don't use rules of thumbs on the internet unless you know that they're accurate. So even measurements from manufacturers will often be off. So the best way to determine how much power a pixel is using is to measure it. Why do we care how much power the pixel uses? Because the pixels use power from the controller, and the controller has limits, and we'll talk about those. So we're going to start at the very end of the stream, at the prop. Now, often you're going to be looking at individual props, and you may have to add up multiple props to get to a final amount. So you may have 50 pixels on this prop connected to this prop, which is 50, and this prop, which is 50, which is 150 total. The power will change based upon, of course, how many total pixels you have. And it is not always linear. So if you measure 50 pixels at 1 wattage or amperage, it may not be the same at 150 multiplied. So always recommend measuring actuals. Now, we also aren't going to talk about percentage reductions. Now, in most controllers, you can set a percentage of output, and that is very common. So a pixel at 100% output, full white, may use 1 amperage or wattage, but at 50%, it may use a different. And it may not be exactly 50% less of the 100%. So this is why it's always good to check that. Now you can set those percentages either directly in the controller many times by going into the configuration, or even within the software you can just tell the software to limit your output. Instead of putting out 100% of the power, it will put out 50%. Now, we are going to use 2 possible numbers, and this really depends upon how you prefer to use your calculations. Ultimately, you can get to the same amount, which is how much power is being used. We can measure that in watts or amps. Now, to get to watts, we need to take the voltage times the amperage, and that will give us our wattage. Now, that's easy because many things like power supplies are sold in 350 watts, or it may say 60 watts per output, or it may say in amps. So, for example, you may have a fuse rating that says 5 amp fuse rating. Now, that 5 amps is going to pass different wattage at different voltages. So, you may have 15 watts at 5 volts and 60 watts at 12 volts, for example. All right, so let's first start with how do you measure just the pixel wattage. And I'm going to, or amperage, actually, in this case. First, we need to know what the voltage is. Now, I've gone ahead and hooked up this string of pixels at the end. What I've got here is I've just got an extra pigtail, and I've just attached my alligator clips to this pigtail, to the positive and to the negative, and I'm measuring 9.5 volts. Now, what I'm going to do is I'm going to go ahead and disconnect that. I'm going to unhook that. I'm going to come over to my controller, and I'm going to measure the power at the controller going in. And you can see it's a nice solid 12.08, so almost exactly 12 volts. How do we get from 12 volts down to less than 10 volts? Well, there's a power drop. And if you want to use the analogy of when you've got a water hose, you hook up one water hose, the water comes out at a certain pressure, you hook up a second water hose to the first water hose, the pressure drops, so you're getting less water out at that end. That's exactly what's happening here. Water in hydraulics is very similar to the way electricity works. So we're measuring this at 12 volts going into the controller, but we have losses that are occurring through the cable, and then of course mainly because the actual pixels are using it. Now, when you're configuring your wattage, you're going to look at the input wattage, or input voltage times the current draw that we'll talk about in a second here. All right, now 12 volts should be going into this pixel right here, then again coming out at, again, what do we have here? Just under 10, right? 9.4 volts. All right. Now, let's measure the current. Now, in the multimeter, and I should mentioned that we need a multimeter to do this. You don't need one like this. Most of them operate in a similar fashion. Most multimeters are going to have several hookups here. You're going to have the common, which is the black or negative. Then you're going to have the voltage, and you'll see a little V here. You'll typically see a V, ohms, and a diode scale. And then over here you have this A for amperage, or milliamps. You'll notice that it has a little drawing between this. So when we're measuring voltage, we measure between here and here, and we're measuring amperage, we measure from here to here. And you'll notice that they're even color-coded. So this is where we hook up our red leads, this is where we hook up our black or negative leads. So when I'm measuring the voltage, I'm on voltage DC. The straight lines mean DC voltage, and we're working with pixels all DC. There's no AC voltage. We would measure it voltage. So again, voltage here. Now, when we're measuring amperage, we have to move our connection over to the amperage side. And then we also need to move our meter to measure amperage. So my meter's telling me, hey, it doesn't like that. Now, what we are doing is instead of measuring a specific point coming out, we're measuring the power going through the connection. So unlike this, where we're just measuring the power when it comes out at the other end, we're not breaking the connection, we're just measuring what's coming out. In this particular case, we need to measure the power before it goes in and then goes back out. Now, in this particular case, I have built up a little cable here. All I've done is just taken an extension cable, and I've passed through the negative data, and I've broken the positive. So in here, the positive and negative actually break the positive line. So in other words, we're just unhooking the positive power going into the pixels, and we're running it through the meter first, and then back out again over to the pixels. So actually here, I'll use my special cable here, and I'll hook that up here. And again, you don't have to build anything this fancy. It does make it easier, makes it safer. What I'm going to do is I'm going to disconnect my pixels here, and I'm going to hook up this test cable here. And you'll see nothing's registering because no power is going through this connection. All right, I'm going to hook these up here. Oops. Okay. So now we are getting our current draw through here, and we're measuring it in milliamps. And I'm going to change the range. So in this particular case, we have a straight A, not a little m or milli. In this particular case, it's giving me 2.45 amps of power are being consumed by this string of pixels. Now, if I go over here to my computer here and I pull up my calculator, and again, assuming we're running 12 volts, if I multiply 12 times, I'm going to multiply 12 times 2.45. We have 29.4 watts of power being consumed by this specific string of pixels. All right, so let me go ahead and just show you that. So it's going to be 12 times 2.45, 29.4 watts. So that's just Ohm's law. You can look that up on the internet. Now, how much wattage per pixel? Because you may have some software applications that can say, oh, wattage calculations, or maybe you just want to put it in a spreadsheet and calculate it by pixel. Now again, you may have more wattage as you use more pixels. It may change. Well, we can just simply divide that. This is 100 pixels, so we're going to simply divide that by 100. And you can see we're using 0.29 watts per pixel. Now, this controller is configured with 100% output. So in other words, we have not restricted its output to something like 50 or 30%. So we're working worst case scenario. I also have the pixels on white. So these pixels are white using the static white test mode on my controller. That's worst case scenario because we use different current when we are using less colors. Because we have a red, green, blue LED in here, we have to have all three on to produce white. That is the most amount of power we can use. So let's go ahead and see that. So I'm going to go ahead and change this. And so we're going to go to red. We can see that at red we consume 1.05 amps. And at green, 1.08 amps. And at blue, 1.06 amps. Sometimes these are exact, sometimes they're slightly off. It's not uncommon that they're slightly off. Depends on the resistors and a bunch of other factors. So that means whenever I'm doing these calculations, I'm looking at worst case scenario. What is the worst amount of power we could use if we have these lights on full white 100%? It's going to be 2.44 amps, which we've determined is 29.4 watts. All right, now let's just go ahead and hook up some more pixels. Now, there is a limit to how many pixels we can hook up in a particular string. All right, so I'm going to take another string here. This is the same exact kind of string, and in this particular case, just 100. Now, I should note that our controller is just defaulted, so there's 30 pixels that are not turned on here because it's set for 170 pixels by default. So if you don't have all your pixels lighting up, that may be your root cause there. All right, now, if we look at the amperage now, we're at 3.25 amps. So again, if we want to get our wattage, we go 12 times 3.25, and that's 39 watts. Now, we have 170 hooked up. Now, these pixels at the other end, even though they're not turned on, they actually get a little power, so there is some slight differences, but we'll say that it's just rounding errors. So 39 watts divided by 170 means 22 or 0.22 watts per pixel. So again, they're not always linear, so once you connect more pixels, you may have different power draws. Sometimes they're close, sometimes they're not. Now, also, it's important to understand not all pixel types use the same amount of power. So let's try some different kinds of pixels. Now here we have some gumdrop pixels, and you can see that these use 0.55. So, and if you go 0.55 times 12 volts, we get 6.6 watts divided by 50 pixels in this string. It's only half what we were normally seeing almost in regular 12 millimeter nodes. These have a reduced output. These are just low wattage. They're used often in props where you have a lot of pixels and they don't need to be real bright because they're so close together. And so we're using nearly half the amount of power in these gumdrops. So let's go ahead and take a look at some seed pixels. So here we go. This is going to be 50 pixels, 2-inch spacing. So we have 0.44 watts, 0.44 amps times 12, 5.2 total watts divided by 50 pixels in the string, only 0.10 watts. Now, is there a difference in brightness? Well, yeah, there is going to be a difference in brightness. So let's actually hook these two strings together here. So it's important to understand that brightness, and we of course have some stage lighting on here that's pretty bright, so it may not be possible to see a complete difference. LEDs are actually brighter because they're linear. Your eyeball is not fully linear. It's the same reason that if you look at a stoplight in the middle of the day and a same stoplight at midnight, it's the same brightness. The light never changed brightness, but its appearance changed. Our eyes don't see light in a linear fashion. So this is actually brighter than this seed pixel. Okay, so now we know how to calculate how much wattage or amperage. Obviously, if you wanted to determine the amperage here in this particular string, if you have 0.44, you would divide that by 50, and you have 0.0088 milliamps of power consumption. So a 1 would be a full amp, and obviously we do not have an amp here. Okay, now what do we do with these numbers? Well, we have to now follow ourselves with these pixels upstream because they have to get power from the controller. So let's take a look at our controller. Now our controller can have various different configurations. This controller has 2 power supplies. Each power supply is 350 watts, which is 30 amps at 12 volts in this particular case. Now this configuration actually has 1 power supply to each board, And you'll notice that there are 2 positive wires and 2 negative wires for each of the 16 outputs. So this is 16 plus 16. So this is 32 total outputs over 700 watts. And what's happening here is that this board, as many are, is broken down into sections. So there's 1 through 8, and this is actually printed on the board itself. It may be hard to see. So this is 1 through 8, and that powers the 1 through 8 outputs, and then this second power wire powers the 9 through 16. Now they come from the same power supply, but they're broken up. Now that does allow you to run one power supply exclusively to just 1 through 8, and another power supply to 9 through 16, or as we have it configured here, as one power supply to one entire board. So what does that mean? We've got some math to do again. So back to our math. If we have 350 watts coming out of this power supply, how much wattage could come out of each one of these outputs? So we take 350 and we divide it by 16, and we have 21 watts per output. Now you could also do it the other way. You could do, if you knew it was 30 amps, you could divide 30 over 16, or, whoops, I'm sorry, 30 divided by 16, which puts you at 1.875 amps per output. Now, that's your limitation. Now, at any given time, we're going to use some simplistic numbers here, because let's just assume that all the pixels are drawing all the same power all at the same time, and they're all white, and they're all at 100%. So again, we're working from worst case scenario here. In that particular case, you can't draw more than 350 watts. So if we're using a string that has, let's say, 29 watts or 30 watts, well, that means if this string is using 30 watts, I don't remember the exact number, and we take 350, clear, 350 divided by, and let's say the string is using 30 watts, that means we can actually run 11.6 strings at max output, right? Now, how could you get more power out to each output? Again, you could wire it so that there were 2 power supplies on each output. So you need to determine, of course, whether or not that's necessary. You want to take into consideration what is the wattage used here, and is there enough power here? Now, you can have it so that, let's say we're not using it equally. Let's say that we have one power supply, but we're only using, let's say, 9 of these outputs. So if we're using 350 and we divide it by 9, that means we can actually use 38 watts per output, because we're not using the additional outputs 10, 11, 12, 13, 14, 15, and 16. So you can see there's a little bit of a moving number here, and it's going to depend upon exactly what props using how much wattage of each pixel and how often they are on what percentage output. That then determines what your power consumption is. Now, you do also typically have a per output limit. So this particular controller has fused outputs, and almost all of them will have some sort of fuse. You should never use a controller with no fuses. That's a very bad thing and dangerous. But let's just assume that your controller, as many do in this class, have a 5 amp output. So they have a 5 amp fuse. Now, well, that's not the wattage. So if we're running a 5 amp fuse at 12 volts, 5 times 12, that means we can put out 60 watts per output before the fuse will blow. Usually there's some play in there. But if our string here is only 30 watts, clearly we could run 2 of these strings together and have it at 60 watts. Now, again, we're using 60 watts out of that power supply. That means we've used up 60 of those 350 watts. So there's not that additional wattage that can be used without additional strings. All right. Now, at that point, we've now determined the total number of strings. Now, your software may be able to keep track of this. You may be able to go into your prop and say, this particular pixel uses this amperage or wattage, depending on your software, and it'll then calculate, oh, okay, you have this prop, I've got it hooked up to this output, and then it may tell you you have this many amps or watts used on a given specific output. So that may be possible. Another common way of doing this is to just simply set up a spreadsheet. This also is very helpful when you're planning out your display, kind of almost like a blueprint for your show. What you might want to do is set up a spreadsheet. Each row is each prop, and then in that prop you put how many pixels. So let's say you have 100 pixels, and then you determine that the wattage, and again you can work in watts or in amps, and you may determine, oh, each pixel uses 0.29 watts, and I've got 100 pixels, so I'm using 29 watts on my 100 pixel count string. And then you can simply then add those up over the entire controller and then determine what your wattage budget is within this controller. So hopefully this video has been helpful to determine how you can calculate what your power consumption is. Key takeaways here are: 1, you can't know what you're going to need in terms of a controller power and the way it's built. 1 power supply per board, 2 power supplies per board, until you know what the pixels and props are. You have to know how many pixels, what kind of pixels, and that power consumption of the pixel, and then how many of those are going to be connected to any given output, and then doing your calculations in total for the controller.